Our video today will be talking about accelerating cloud computing using RDMA. Our group is groups 7 and 9 in EE533 for Professor Young Cho's class. Our group members are Yuelun, Songyu Huang, Weijie Lin, Qian, Liu, and Bennet Cowdin. RDMA tackles the issue of the inefficiency of computer systems. And computer inefficiency, in many ways, is similar to issues we find at hospitals every day. Let's say you had a nasty fall and broke a bone. You would be transported to the hospital in an ambulance, or maybe by a family member, but only to find a long wait for the emergency room, in some cases up to a few hours. This wait is caused by an overworking of the bureaucratic systems of a hospital, as they have to check in patients, assess how serious their condition is, and then send them to the correct medical professionals to treat them, but only when they're ready to receive patients. Instead, what if when you were first injured, your family or the paramedics could pre-schedule the correct doctor to see you, completely bypassing the hospital bureaucracy and eliminating or greatly reducing the delay until treatment, which hopefully would improve your outcome and hasten your recovery. RDMA works much in this same way, bypassing a computer's internal bureaucracy to speed up communications and free the computer's resources to work on other tasks, providing increased speeds in everything from cutting-edge medical research to your home internet.
We are entering the era of cloud. Modern applications such as car sharing, online shopping, and mobile payment use cloud computing to process the massive data from their millions of users. Adoption rate of public cloud service by enterprise are increasing. The net income of cloud service business was also growing rapidly in recent years. Microsoft Azure has as much as $21 billion of income last year. However, people are realizing that communication across computer clusters is the bottleneck in cloud computing, and RDMA can accelerate communications aggressively. Therefore, cloud investment for new RDMA equipment will be much more important, and Mellanox, a company that specializes in RDMA network products, is turning out to be a hot takeover target. It generates $300 million in revenue and made $40 million in profit in one quarter.
RDMA provides a high throughput and low latency between the server and the client, which is an ideal tool to improve the throughput of high-performance machine learning centers. There are several ways to implement RDMA. InfiniBand, ROCE, IWARP require hardware support, while soft ROCE and soft IWARP are software RDMA implementations. All of them can provide different benefits and drawbacks. We need a special RDMA NIC or switch to support InfiniBand, which makes it incompatible with ROCE and IWARP, and very expensive to implement. In contrast, the soft ROCE and soft IWARP do not need hardware support, but do not get the same performance as hardware RDMA.
We provide two high-level APIs for programmers. RDMA read has two inputs. They are the address where we are reading from, the length of the data we desire. RDMA write has three inputs to tell our network processor to where we are going to write, from where we are going to write, and the length of data we are going to write. Here is a C-style example code of using RDMA. After the programmer issues such a command, our library will automatically generate a RDMA packet. It has an IP header followed by our customized RDMA header. Our RDMA header is composed of a RDMA control byte, which specifies which command the packet is, and a RDMA address, which specifies which data in the distributed memory system we are trying to access. If it is RDMA write, we attach the data that needs to be sent as payload. Our RDMA-enabled network interface card is then able to speed up the communication by a significant margin. After the RDMA packet is sent, our network processor on FPGA will decode the packet and recognize that it is an RDMA packet. It will then trigger a specific routine and modify two hardware registers to tell which command it is and what address the packet is trying to writing to. If it is an RDMA write packet, instead of going through all the unnecessary memory copies and data queues, our customized driver will read from those registers and bypass operating system and directly deliver the content to user application. If it is RDMA read, the driver will also bypass kernel and directly DMA the requested content into our network processor and modify a software register to tell the network processor it is RDMA packet. The processor will automatically add a header to the content and forward the packet correctly.
Let's talk about our network processor design. We used parallel dual-core design for our processor. In this design, we use a state machine to achieve the functionality. The first and second packet will go into two cores separately and be processed by our dual core. When third packet comes in, it will check which core is free or busy. When it detects the free core, the third packet will be processed. Finally, when each core finished its job, it will output the packet automatically. In this way, we can double the bandwidth by dealing with two cores at the same time. For single core, we used 4 threads fine-grained pipeline design. With 4 threads, we can avoid stalling because of the dependency problem. We designed our main memory as FIFO to receive the outside data. When packet was received, our processor will deal with it at high speed. For our processor, we used RISC-V as our instruction set. There are many reasons to use RISC-V. Using another ISA such as x86 or ARM will require purchasing the license and it is very expensive. On the other hand, RISC-V is free to use. It is also very customizable. We can add our own instructions to realize the application-specific functions. RISC-V is also known for its low complexity and high performance. Not only good for some big designs such as cloud computing, but also be suitable for some small and low power chip. Nowadays, the RISC-V has an expanding community. We will get increasing community support in the future. In our design, we define 2 special instructions. Instructions store hardware register will store the input data of FPGA, like read or write command, address, and data into specific hardware register. Then driver will read these hardware registers and store data into memory directly. Instructions load software register will load the read or write state into software register to allow our processor to change the states in the state machine. By using these 2 special instructions, we can realize the bidirectional communication between kernel and FPGA to realize the function of the RDMA.
Now, let's see what we can really gain from this. In our experiment, we first install a module on the server node to allocate 1 kilobyte memory and fix it there so that the logic address will not change. Then map it to the user space and store some data in this space. Now the client node can send the application to read the address of that data we stored and measure the time. And the result is shown here. We have tested both the software-supported RDMA and the hardware-supported RDMA. A traditional network communication has 339 microsecond delay, while our RDMA method costs only 278 microsecond delay with software acceleration, and 105 microsecond with both software and hardware acceleration. So we get 20% speed up and 68% speed up respectively. Due to the limited number of net FPGA, only the server side is equipped with this system, which means it could be even faster if both sides can have this product. Now we are going to present how to set up the environment and test the system.
To set up the environment, first we need to get the root access. Then we enter the folder that stores the driver source code. As you can see, we have already deleted the NFC control file, the driver file that we're going to modify. Then we create a new NFC control.c and paste the modified code and save and exit. After we compile the modified driver, we remove the previous driver and install our modified driver. Then we use a Python script to reset the system and then download the bit file we have to our FPGA. The final step of our setup is initialize the instructions in our network processor using loadins.py script. To test our RDMA write functionality, first we use mmap to write some random data into the physical address 0x3000, and we display the content here. Now we send a RDMA write packet that contains a lot of zeros as payload. Finally, we use mmap to read the content of physical address 0x3000 again, and as you can see, the RDMA packet was written successfully. To test our RDMA read functionality, we first send a RDMA read packet to the control node and use TCP dump to monitor if the control node successfully returns a packet back. As we can see, the control node returns EE533 response correctly as we expected. Finally, we want to measure the latency of RDMA. First, we send a RDMA read packet and measure the runtime delay of RDMA return packet. We will perform this experiment many times, and as you can see, the latency is averaged about 100 microseconds, significantly faster than 300 microsecond delay not using RDMA. This is the end of our video. Thank you for watching.